Hey everybody, welcome to a brief introduction to WebAssembly. In this video, I'll be going over the history of the WebAssembly language. We'll discuss some of the things that make WebAssembly a great language, and we'll focus a bit more on its standout features. We'll then do a code demo where I'll be using WebAssembly to solve one of the exercises on the WebAssembly track on Exercism, and we'll then move on to a listing of the resources that you can use to learn WebAssembly. I'm really excited about WebAssembly and I'm going to show you what it's all about. So let's get started. WebAssembly, which is often abbreviated as WASM, was designed by the W3C standards body for web technologies. Its design goals were to have semantics that are fast, safe, and portable, and a representation that is efficient and portable. So why have WebAssembly at all? Well, back in the days, executing things very fast on the web was usually achieved via very specialized browser plugins. You probably have heard of Flash, Silverlight, which were proprietary plugins that would focus on allowing high-speed execution of code in the browser. They were much faster than regular JavaScript in the browser, and that's because JavaScript as a language has certain design decisions that make it less suitable to high performance computing. And Flash and Silverlight could work around that because they were, well, custom built. There were major downsides with these plugins, and several of the bigger downsides were security and that they were not standardized. So especially Flash had a history of being somewhat of a security issue for people. People wanted to get rid of these proprietary browser plugins, but JavaScript was sort of hard to optimize. So what Mozilla then did is that they designed WASM.js, and WASM is like assembly. So it was an assembly-like version of JavaScript. Well, what does that mean? So what they did is they took the JavaScript specification and they picked out all the parts that they thought could still be used in a high-performance scenario, and they basically ditched everything that was hard to optimize. So you had JavaScript, regular JavaScript code, but you only used parts of the JavaScript specification that were amenable to high performance computing. And with this subset, the performance that you could get out of JavaScript was actually quite a lot better than what you would get from default JavaScript. And the main reasons how they achieved this is via type consistency, which means that there was no dynamic changing of types. So in principle, in JavaScript, the type of a variable can change any time. So if you have a loop and at first you have a variable that's an integer, at the end of the loop, it could very well be a string. And that is hard to optimize. But the subset of JavaScript that WASM.js chose did not allow for this. So that was a great boon. And they also selected the features that didn't require garbage collection. So languages could compile to WASM.js. You usually wouldn't write directly in WASM.js yourself, but you would compile to WASM.js and still get good performance when running on the web. It was still JavaScript, of course, so it is limited in what it could achieve. And that's why the W3C body thought that it would be better to just come up with an entirely new proposal and take what was learned from WASM.js, and that became WebAssembly, WASM. As the name implies, WebAssembly is an assembly-like language, and that means that it contains instructions that are executed. There is a difference with regular assembly languages, though, because WebAssembly is crucially not tied to a specific CPU, which is the default for assembly languages. That goes back to the portable design goal. So WebAssembly is a platform agnostic instruction set. It also means that for each platform, for each CPU, you have to make a translation of the WebAssembly instructions to actual machine instructions. And this thus requires a virtual machine. So WebAssembly is machine dynamic. I mentioned before that you can change types on the fly. That's not the case with WebAssembly. WebAssembly is statically typed. The compiler knows beforehand which types have which variables have which types, etc. Another difference is that WebAssembly uses a stack-based programming paradigm, So you basically, everything that you do is putting things on the stack and popping things off the stack via certain instructions. So addition means putting two numbers on the stack and then an instruction to, I don't know, maybe add those two numbers. So those two numbers gets popped off, the instruction gets popped off, and the result of the addition is put back on the stack. So it's a different way of thinking about your programming program. WebAssembly uses, I mentioned the compiler, it uses an ahead of time or a just-in-time compiler. It could be interpreted, but usually WebAssembly is compiled beforehand. And that is a difference from JavaScript, which is interpreted. It's an open standard, as you can expect, having been designed by the W3C, and it defines two things. So you have a binary format, which is what actually gets executed by the virtual machine, and there is a text format that you could use to write in, which is then compiled to the binary format. And for our code demo later on, we're not going to use the binary format because that will be somewhat hard to read, but we're going to use the text format. But just keep in mind that the text format is just a intermediate to the actual binary format. So you can write text format, but what gets executed is always the binary format. I mentioned that there has to be a virtual machine for WebAssembly, and it has implementations in all major browsers, so that's good. So you can run WebAssembly on all the major browsers, and well, as we see later on, you can even run it outside of browsers, but we'll get to that later on. So where is WebAssembly used? Well, in many pages that require high performance. So prime examples being Google Earth, Figma, Unity, AutoCAD, those all require a lot of performance, so they use WebAssembly heavily to get the best performance. It has also been gaining traction on the server side. So for example, to run microservices or run on SaaS platforms like Cloudflare Workers or even in Docker. Let's look at some of the reasons why WebAssembly is a great language. First of all, its stack-based virtual machine is quite a simple and lean specification. And this makes it an easier target to implement. So if you want to compile to the WebAssembly virtual machine format, so the binary format, that is relatively easy. And it's also relatively easy to implement such a virtual machine because of its well-defined and simple semantics. A second great feature is that WebAssembly text format uses S expressions to allow you to write in what appears to be an imperative style of programming, which most people are familiar with, but whereas under the hood it's actually compiled down to the stack-based format that WebAssembly uses, but you need not be aware of that. So if you've ever worked in a Lisp language, you'll know S expressions because that is what Lisp languages use for their syntax. And if you haven't ever worked with it, it's just parentheses to indicate the structure of your code. And we'll see an example when we will be doing our code demo later on. A third great feature is that WebAssembly has a strong interrupt story with JavaScript. So, of course, WebAssembly and JavaScript work in tandem a lot. So if you want to pass data from and to WebAssembly between JavaScript and WebAssembly, that's easily possible. There is something called linear memory, which allows you to reserve a block of memory, and you can use that in JavaScript, and we'll show an example of it later on. But just remember that there's a lot of ways in which you can interrupt fairly easily between JavaScript and WebAssembly. There is one important caveat, and that is that WebAssembly doesn't allow you to manipulate the DOM, so the document object model. So if you want to, I don't know, create a DOM node, you can't do that directly from WebAssembly. You have to shell out back to JavaScript. So that is one important thing to keep in mind. A fourth great feature of WebAssembly is that it's being continuously improved. So not only the virtual machine is continuously being improved and tweaked, but the language itself too. So there are tons of new features that are being proposed. It's all in the open, so you can follow it if you like. But in the future, you might expect features such as threads, garbage collection, which is actually in some browsers already, SIMD related instructions for high performance instructions working on a lot of data at the same time, tail call optimizations, and many more. They will still try to keep the language simple, but some of these features will make it more amenable to a target for different languages. For example, tail call optimizations are a great boon for a functional language compiling to WebAssembly. And the last great feature that I'd like to mention is that WebAssembly is actually, unlike most assembly languages, quite a safe language. So there are very strong security guarantees, safety guarantees when you run WebAssembly code. As I mentioned before, the spec is very fixed, very rigid, very clear. Clear semantics are a great thing because you can write tooling to verify the semantics of the code. As an example, when you call a function, the function that you declare defines its parameters and its result types. And then when you try to compile the program, it will check if you have the right values, enough values, but also of the right type on the stack. So if you want to do integer addition, you have to have 2 integers on the stack. And the result will be that those 2 integers will be removed off the stack, popped off the stack, and then the result of the addition is pushed back. So the WebAssembly compiler will know that calling the integer addition instruction means that you have to have at least 2 elements on the stack, and it will in the end return 1 new value on the stack. So the other ones are removed. And with this way, the compiler will actually check at compile time if you are calling functions with the right amount of data on the stack. So this also goes for a return value, where if you have to explicitly return things. And if you have too much on the stack, you have to be explicit about that. Otherwise, you will get an error. And we'll show this in the code demo. But it also holds for a control flow, where you can't just move to any location in the source code. So if you have programmed in an assembly language, you often have jumps. So on jumps, you can jump to any label that you can find. So basically, you can go from anywhere to anywhere, which is very useful, but it's not necessarily very safe. And WebAssembly is much more like a conventional language, where you have just structured control flow. So if you have a loop, you can just stay in the loop, but you can't just jump anywhere. And another great thing about WebAssembly is that it runs in a sandbox environment. And this means that basically when it runs, it's shielded from other WebAssembly code that's being run. So there is no way in which they can interact with each other and do possible harm. Let's look at the standout features of WebAssembly. First of all, WebAssembly is very efficient. Its binary format is compact, which means that it's fairly small, especially compared to JavaScript code. The binary format can also be decoded, validated, and compiled in a very fast single pass, so you don't have to iterate over it more than once. And a fantastic feature is that it is streamable, where if you get a chunk of WebAssembly data to the compiler, it can also start with decoding, validating, and compilation before the rest is received. And that's a major difference from JavaScript, which basically you have to get the entirety of the file before the compiler can actually do anything with it. But with WebAssembly, the streamable bit means that if you push a bit of data, the compiler can already start working on it. This also is great if you consider that WebAssembly binary format can be compiled, validated in parallel. So you can do a lot of stuff without waiting on other stuff to finish. All this makes it a great way of writing high-performance web applications. A second standout feature is that WebAssembly is a great compilation target. And even though we are going to do this shortly, you normally don't write WebAssembly directly yourself, but instead you would write code in another language, and that would compile to WebAssembly. This has a couple of benefits. For example, that many languages that you know can also run on the web. So without actually you having to learn another language. Most major languages nowadays support compiling to WebAssembly, and new languages are of course added regularly. So you don't have to write JavaScript, you can just compile to WebAssembly, and then there's a little bit of glue code needed. But in general, many of the major languages can now run in the browser directly without having to resort to any of the plugin shenanigans that we mentioned before. So there are basically two strategies that languages can choose when trying to target WebAssembly with their language. And one is that they directly compile the entirety of the source code to WebAssembly. But that has some disadvantages because, well, for example, there is no garbage collection yet in WebAssembly. Another option is to compile the interpreter or the runtime to WebAssembly and then have that run in the browser, and that can then run your regular unaltered code. So, for example, if you have a C# which compiles to bytecode, that bytecode could be interpreted in the browser by the WebAssembly compiled runtime. So you don't need to actually have your own code be compiled to WebAssembly because the interpreter has been compiled to WebAssembly. So there are different models, and it depends on the language which one they choose. A third standard feature is that WebAssembly is easy to deploy and run. All you need basically is a virtual machine that can interpret the bytecode, which is, as mentioned before, quite simple in a lean format, and all major browsers include one. But this ties into the next and last point, is that it's not only tied to the browser. So WebAssembly can also run server-side. There is a specification called the WebAssembly System Interface, or WASI, and this is an interface, both an ABI, Application Binary Interface, and API, Application Programming Interface, and it's designed to be portable to any platform. So Windows, macOS, Unix, you name it. It's quite similar to POSIX, which is the standard interface for Unix systems, and it provides things like I/O, so opening a file, web requests, whatever. The key part of WASI is that security has been one of its primary concerns from day one. So security is part of its design, and this includes sandboxing that we already mentioned. So the running of WebAssembly code in compartmentalized bits of memory, so without any options to access other bits of running WebAssembly code. But it's also capability oriented, which means that by default, you're not allowed to do much. So if you want to read or write to a file, you have to explicitly say that these are the capabilities that I want to use. And that could then be, depending on what application is running WASI, you could, for example, be prompted, do you want to allow this program to access files? And that is completely different from how regular machine code works, and even how most other languages work. So this capability-oriented feature has a lot of benefits to security. Another key aspect of WASI is that it, in principle, allows to be the glue between languages. So if you have two languages that can compile to WebAssembly, WASI could be used as the intermediate. So you could easily interface from, I don't know, a C# to a C++ without having to do anything, basically, because you can get everything for free with WASI, because that is a shared specification between C++ and C# then. So to stress this point, Solomon Hykes, who is a co-founder of Docker, wrote in 2019, if WASM plus WASI had existed in 2008, we wouldn't have needed to create Docker. So that just goes to show that this is truly transformative, and we will be seeing a lot of WebAssembly in the future. Let's start writing some WebAssembly text format. What I'll be doing is I'll be solving the Hamming exercise. And the Hamming exercise is one where you get two strings, and those strings contain letters. And those letters are C, A, G, and T. And then what we do is we compare these two strings by index and sum the number of places where they have different letters. So consider this example, two strings. You can see here that at the very first position, the first strand has a G and the second one has a C. So that's the difference. So we count one. This is the same, so still one. The third one is different, so it's 2, 3, 4, 5, 6, 7. So in this case, there are 7 positions with different letters, and therefore the Hamming distance is 7. So that's what we're going to do. there is some stuff here that is usually not in the exercise, and this is WebAssembly specific. It's about which parts of memory we need to use. But for now, you can forget that, but just remember that we'll come back to this later on. I will be doing the code demo in Visual Studio Code, and I have installed the official WebAssembly plugin. And this extension is a fantastic way to get syntax highlighting, but also a bit of code completion. And we'll see how useful that is in a second. Then we'll have a specification file. So you get test cases. And the first thing that you might notice that this is all written in JavaScript. So in order to work with the WebAssembly track, you are actually using JavaScript to interact with it. So the tests are all written in JavaScript, and that under the hood, we will do WebAssembly compilation. We'll see that in a sec, but just we'll go over all these tests one by one. We'll do a very test-driven development way of building this exercise. This is our stub file. So the stub file is where we start out with, and we see a couple of things. So we see a thing called a module. So that's like a grouping of functionality. And then within that module, so within its parentheses, we define a bit of memory. And we can forget about this for now. We'll come back to that shortly. But let's focus on that we have a function here. So func defines a function. And export compute means this function is exported by this module under the name compute. So this is like saying to the outside world, you can call this function via compute. And that's the name. Then there are four different parameters. So you have first offset, first length, second offset, second length, and then a single result. Okay. So why do we need, where's string? Where I don't see strings. And you're right. That's because WebAssembly doesn't really have strings, at least not yet. So what WebAssembly does have, it has memory. And in memory, you can have offset. So you can think of a string as a series of bytes, which is actually, it is. So a series of integers. And then this offset is the position of the very first element in the first trans string. And then the length is the number of characters in that string. And this is very, well, I would almost say C-like, where you have a position to the first element and a length. And those two things combined allow you to iterate over the string. Of course, we have to do the same thing for the second strand too. So second offset, second length. And then finally, there is just a single value that we return. And that leads us to the next point, is that this is a type. So this is a signed 32-bit integer. So all the parameters are 32-bit signs. But just remember that you also have other types too. And we have to be very explicit about which type we are using. So let's look at the body of the function. And if we look at the body, we have to remember that we are working with S expressions here. So these parentheses are defining the scope of the function. So things within these parentheses all have to do with function. And similarly, things within these parentheses all have to do with the module. But this is a separate thing. So what is defined here isn't necessarily linked to here, although we can use it in this case. But just remember that those parentheses are really key in identifying the structure of your code. So how do we return something? Well, we remember that WASM is a stack-based format. So when the compute function is being called by JavaScript, it will see just the WebAssembly runtime will see just this single instruction, and it will run that. So what is the result of i32.const42? Oh, basically, it's pushing a value on the stack. So initially here, so the stack is empty. But after executing this instruction, the stack looks like this. So the WebAssembly runtime then knows that there's a single result value. So there's just one value on the stack, so this must be the result value. So let's just see what happens if we run the test. We do that via npm because our tests are in JavaScript, and we can see that it fails and that it expected it to be 0. So the spec is two empty strands, must have a distance of 0, but it's actually received 42. So and that makes sense because that's the number that we pushed on the stack. So if we change this to, I don't know, 17, run it again, you'll see that we get 17 as the value. So this is the stack-based model, but you sort of have to trust me that this is true. So what happens if we do 17 and then 5 and then run our code again? And this time we get something differently. It says error compiling the what file. So it says expected 1 elements on the stack for fall through, found 2. Okay, so let's see what happened. Previously, I have to also update the comments, which is why sometimes comments can be bad. But after executing this instruction, the end result of the stack will be 2 values on the stack. So the top value is 5 and then there's 17. But we said that there should only be 1 result value and we have 2. So the compiler knows at this point before running our actual code. So this is happening at compile time, and that's very important for our safety guarantees. So the compiler will see that, hey, the end result of the stack, the number of elements on it, doesn't match the number of elements that are expected to be returned. So there are a couple of ways that we can work around this, of course. We could, of course, just remove this. What we could also do is we could do return, and return will allow us to see now it has 5 and basically says if there are at least enough elements on the stack that you can return, we'll just return that the first value or the first n values depending on the return type, and we'll just discard the rest of the stack. So this is sort of like a safety mechanism, but whether or not you want to use that, that's up to you. But for now, just remember that a return could be useful, and a return will be useful later on for flow control. But these are the basics. We started with an empty stack, and then instructions do things with the stack. So as a third example, let's just do i32 dot, and we can see that we have a lot of different instructions here. We need not go into all of them, of course, but let's just do addition. So unlike other languages, non-assembly like languages, there are no arguments to the addition because the add instruction just assumes that there will be 2 things on the stack. So if we run this, maybe have a think for yourself what the result will be of running the test, and then see if it matches what we have here. So give you 1 second, and then we'll scroll up, and we'll see that it's 22. So the end result of calling this instruction will be that the stack is, so the 17 and the 5 will be popped off the stack, and the new values, the result of the addition, will be pushed on the stack. So now we have the single value 22. And this is the basic mechanism by which you execute WebAssembly code. You have instructions. Those instructions do something with the stack, or maybe with memory, as we'll see later on, but most of them will do something with the stack. And then in the end, what gets returned is also on the stack. So must be on the stack. So we have now a couple of instructions that show you the stack-based model of WebAssembly. Okay, so I think it's now time that we actually do start implementing things. So to get the first test passing, we could, of course, just return 0. So let's just start doing that. I'll get rid of these bits. Maybe we leave them here for now. And we get at least 1 passing test. So hooray. So let's move on to the next one. Single letter identical strands. Okay, so this will of course fail because, well, we haven't done anything. Oh, well, it does. Well, that's convenient for us. We get a passing test. But if we run this next one, we should get a failing test. And now we do. Okay, good. We can't just have our default implementation work like that. So this means that now what we have to do is we have to read those values into memory. So I'm going to get rid of this bit. What instead I will be doing is remove this. So we have to have some way of reading the very first letter. We're not going to do a loop. We're just going to read the very first letter. So we're going to start with i32.load. And then there are different types of loads. So by default, load will load a 32-bit integer. There's a one for a signed 16-bit, and there are signed and unsigned 8 bits, so 1 byte. And in our case, the string array is encoded as 8-bit integers. So we have to load an 8-bit integer. So this is the instruction that we need to load. But what do we need to provide it with? Well, where do we get the data from? Well, that's a good point, because we have a way of defining the things in, so the string is defined in JavaScript, so it's defined in the spec, but we have to bridge the gap to WebAssembly. And the way that we transport data is via linear memory. And our linear memory is declared here. And this says there is linear memory exported under the name mem, which is how the JavaScript code can access it. And it has a size of 1 page. This means 64 kilobytes. So we have access to linear memory, and you can think of linear memory maybe as an array. So just a bunch of memory, and you can access it by index. So at most 64K, but we won't be needing 64K for this example. So we know that this parameter, the first offset, is where we get our data from. So we basically want to say we load the bit of memory at this offset. So load 8 will then need an offset. And then we can do we have to get this value. And this is not just passed on the stack, so it's not yet there. We have to load it on the stack. So what we do is we do local.get, and then we type in its name. So this will mean that after this will be the value of $first offset. So and that is what gets passed in. So we don't know that yet. That's the parameter. And then afterwards, load 8 will mean that the value is read, so it's popped, and then it's not the value of, but the value at first offset. So this is that's the actual character. So we can load the first character, and just maybe it's good to just run this and see what the value is. So it says expected 1 received 71. So why does it say 71? Well, if we go to the ASCII table, you'll find that 71 is a G. So you can see here, if we go up a bit, you can see here for an A, it's 65. So these are the ASCII values of the characters. So this means that our loading of the character was actually correct. So we now have the array, we have the character is, in this case, it was 65. That was A. So that's the first bit. And we can do the same thing with the second offset. So then our stack looks like value at first offset, comma, value of $second offset. Then we do the same loading, and I get so now we have on the stack we have 2 values. So it's the integer value of the first character, and it's the integer value of the second character, an integer being an 8-bit value. Now we need to see if they're different. So there is a command called i32.equal or not equal. Well, what do we need? Well, it depends. We could do equals. So we're going to say if i32.equal will expect 2 values on the stack, and there are 2 values on the stack. So let's just see what this will do. And we can see here that single letter different strand expected 1 received 0. So that's okay. It's basically inverted now. And that makes sense because we say if they are equal, it's true. And true in WebAssembly means a 1. If it's false, it's a 0. So if we flip this to not equal, that means that if the two first characters are unequal, 1 will be on the stack, so that's true. And if the two first characters are equal, 0 will be on the stack, which is false. It happens to be that the different distance is also, when they're not equal, it's 1. So this should actually match. And now we have a very first working version that compares the very first two characters. Okay, we have an implementation that works for strings that have 1 character. So let's see if we maybe can do something differently. We could continue with the test, but then we get to looping and I want to postpone that a little bit. So instead, what we're going to do is we're going to focus on the error cases. So this is, let's enable this one. This allows first strand longer. So we're now checking whether or not the strings have the same length. And if they don't, we have to return -1. So this is conditionals. So for conditionals, what we need is if statements. Well, how do we do that? So we can just for now ignore that. We're going to move up here. And we have two parameters that actually contain the length. So the first length and the second length. So let's start by doing local.get $first length. So we'll just move this up here. And then after this, we have a value of $first length. Do the same thing for the second length. And then basically what we then, and copy this one. So what we now need to do is we need to check whether or not if they're unequal, then we need to return. So we previously saw that we have a command for that, an instruction, i32.not equal. So this means that the stack is whether it's not a single value. So it will be 1 on the stack. So if it's true, and if it's false, it will be 0. So now we can do an if. So if what is on the stack is true, which means that they have unequal lengths, then we do something. Basically, we do a short circuiting. So we want to return. So we can just return the value that we want. So we're going to say i32.const -1. So this is coincidentally also the reason why this has to be an unsigned integer, because a signed integer, unsigned would not allow us to use -1. And then we say return. And then we stop with end. And then if we run this, we're basically saying, hey, just return -1. And this works. So if you're unsure, no, I'll have to move this up here. So this is the value of the stack. The if statement will then evaluate this. And then if its value is 1, so true, then it will run this block. And then we push 1 on the stack and then return that. So this is now working very nicely. And in fact, we should probably also get this one to be true, this one to be true, and this one to be true. So 4 test cases at once. And we do. So we can see that we now have if conditionals in our code. And that works nicely for us whilst the rest is still working. So we're now getting to the meat of the issue where we have to be able to process these strings of more than 1 character. But before we start focusing on that, I want to do a bit of refactoring, as that will allow us that will benefit us shortly when we try and write the loop. So I'm going to get rid of these comments a bit. So to make this all a bit smaller. So get rid of that, get rid of that, get rid of that. Okay, run the tests. Still all work. So I've not really done much here. But at this point, I'd like to do somewhat of an interesting refactoring, because I mentioned before that we use S expressions, so these parentheses bits. But this is clearly not using parentheses, but it's a stack-based model, so it's what actually gets executed. So this maps one-on-one to how the WebAssembly virtual machine runs things. But it's not necessarily the easiest way to write, especially if you're not used to this. So this, hey, not equals being there after the operands, that's not how you would write it. So in most languages, you would write if x not is y or something like that. But you'd start out with the if, and then you'd have the condition, and then the condition would have arguments. But we have it somewhat differently here. But instead, what we can do is we can use the S expressions to actually sort of make this appear to be imperative, whereas it isn't. So let's start with, let's just do this if. So instead of doing it like this, I will just make this a comment. What we can do is we can start an S expression, have the first thing be an if, and then what is its argument? Well, that's actually this bit. So what if we converted this into an S expression too? So we can start with the instruction that we need, and then we can just have two other S expressions as its argument. So I'm just going to convert it to this. And it's very important to know that this is actually the very same thing as this. This is desugared. So when it is being compiled, the compiler will actually translate it to this. And there is a command that you can use, desugar dash what dash desugar, so you can see this happening. But for now, just remember, this is saying, hey, there is this command, and these S expressions have to be evaluated first in this order. So first run this, then this is being run, and then this entire thing is being run. So this is a more imperative version, and to many people this will be easier to write. So we'll get rid of this. We'll make this the argument to the if, and then in the desugared way, we previously didn't have it. We have to have some a specific S expression that starts with then, and then sorry about the pun. We have to run the code that we want to have here. So this was this bit of code, but we can actually desugar this too. So instead of having it like this, we can do return, and then the argument of return is this S expression. So I hope you can forgive me about the parentheses, but we've converted a lot of our sort of stack-based code to an imperative version. So we're saying if this is not equal, then we return this S expression. And it's completely the same version. So if we run this and I didn't make any mistakes, it should still all pass. So that's great. We can, of course, do the same thing here. So if we do this, oh, by the way, you can also just do this. That's the exact same thing. So this is an S expression with just a single instruction, and it will run fine. And then if we do the load 8u with just a single argument, we do the same thing here. Oh, sorry, same thing here. And then we can use these two things. Oh, I forgot some parentheses here. And then these could be arguments to not equal. So we've rewritten it. So now we're saying, hey, this is like the implicit return the result of executing this instruction after this S expression has been evaluated, and then this expression has been evaluated. So it still all passes. And you can see how beneficial this format can be in reducing the amount of code that we are writing. And now it's time to address the elephant in the room, looping. So I'm gonna enable this test, and then we have to start thinking about looping. Well, looping is defined via loop. And what we do, we give it a name. So we're going to say, I don't know, dollar loop, just a very silly name. You can probably come up with better things. And then within the loop, we have to do comparisons, etc. In the end, we can use a different command to go over the loop. But for now, we're going to have to move this bit of code here. And well, what do we actually need to do? We need to keep track of the distance. So how do we store the distance actually? Well, what we can do is we can define a local variable. So I'm going to say local, and then we're going to give it a name. So we're going to say $distance, and we have to specify its type. So we're going to make it an I32 because that's what our function returns. And then in the end, we're going to return local.get $distance. So we haven't done anything with the looping. And if you just remove that one, we're basically saying, hey, there is a local value, and in the end we return it. Note that this is initialized to 0, so that's important to know. But let's start working on the loop. So within the loop, for every character that is different, we have to increment the distance. So what we can do is, well, the not equals was already giving us the result. So what we could do is we could say local.set. So that's updating a local variable, and the variable is the distance. So what do we need to update the distance with? Well, with the result of this expression. So that's at least one argument. And then we have to increment it. So we're going to say i32.add, and that's actually containing this bit. Let me see if I get my parentheses right. So we're going to say, hey, give me the current version of, I'm going to go through this very slowly in a second. So this is what we want. So we're saying within the loop, update the distance, set the distance to the result of adding the current distance, so the distance that we've already found, with the result of the not equals. And not equals is 0 if they're equal, and it is 1 if they're unequal. So this is either adding 0 if they're equal, so that's fine, the distance remains the same because they're equal, and if they're not equal, we're adding 1. So that's also exactly what we want. So that's a great first step, but we're not really looping yet. So how do we do that? Well, we are also not actually going over the characters. So you can see here, this is just the first offset and the second offset all the time. But let's just see what this would look like if we would actually loop. To loop, we're doing branch if, and then what is the condition that determines whether or not we're done? Well, it might be just that we need another local variable. So with the index, so we're going to say local $i, going to give it a type i32, and this will be your regular C like for loop I. So it will start at 0 and then up until the length. So we're going to say, well, what do we do? We're going to say at the end we have to branch if the I variable is, what is it less than the length? So, well, that means we have to do less than, and we can do signed or unsigned. And let's just do signed. If I is less than the length of the first strand, and we know that the first and the second length are equal at this point, so it doesn't matter which one we're using. Then we branch to the loop. So let's go over this in a bit more detail, and I'll just do a bit of reordering here. So at the end of this loop block, so once again we have the scoping being done with the S expressions. It says go back to the beginning of the loop, so from here to here, if this condition is true. So if $I is less than the length. So this will endlessly loop because we don't yet change I. So we need to do something about that. So we're going to do local.set $I. So this is basically the I++ part of your C loop. So we're going to say the old value of I. Oh, we have to add it. I32.add with the constant 1. So this is increment I plus 1. So set I to the result of adding the current value of I with 1. So we're now incrementing, so that's good. And then the only thing that we don't yet do is to modify the offset. So instead of having just the offset, we have to add I to it. So we're going to do I32.add, so the local offset, with local.get $I, and do the same thing here. Okay, then do this I32.add, and then here local.get $I, and I think we now have we might have a loop version that actually works. So let's just try. Hey, and it works. And there's one skipped one, so we can probably just enable it. And it works. So let's just go over this again. So the important part is if we have some sort of variable-like thing, we define a local. And local, as the name implies, it is only available within the function. So we have the value that we want to compute. So that's like our intermediate value, and in the end it will be our return value. So in the end we return our local, and we have a second variable which is the iteration offset. So we start at 0 up until the length minus 1. Then we do an if statement. We know that. So if the lengths are unequal, then we do a short circuiting. We return -1. And then comes the big loop. So first part of the loop is to compare the characters at the offsets plus I. So this is start out with I is 0, so that will be the first character. Then in the next loop I will be 1, so the first character, the second character, etc., etc. So we are incrementing the distance with the result of not equals, using the fact that it's not equals is a Boolean operator, but it just returns an integer. So 1 for if they're unequal and 0 for if they're equal. So this is basically adding 1 if the characters at index offset plus I are unequal. Otherwise it adds 0, so nothing happens. Then we increment I with 1. And then in the end we say, hey, keep on looping. So return to the beginning of the loop if this condition is true. So if I is less than the first length. And in the end we return the distance. So this is another way to write things in WebAssembly where we use S expressions. And you can see here that even though it's still verbose-ish if you compare it to other languages, it is much less verbose than using the unsugared version with the just all the operands. I could show you the code by using what desugar and then Hamming.what, which will do the desugaring for us. And you can see that it will be quite big and not as readable by far, because we get the nice destructuring thing. And in general, I would highly recommend you just trying to use the S expressions sugared approach, because it will make reading the code a lot easier. Let's look at some of the resources that you can use to learn WebAssembly. First of all, you can of course learn WebAssembly on Exercism. The WebAssembly track has you writing WebAssembly text format in a wide variety of ways. So you have to write loops, you have to do arithmetic, you have to read from and write to memory. So basically a lot of the things that are in the WebAssembly spec, you need to work with in the WebAssembly track. And it's a great way to really get down to the details of the WebAssembly language. Then there's a page called Understanding WebAssembly Text Format, written by Mozilla, and it has a fantastic introduction to the text format. So you get things like what are S expressions, what does a type signature look like, etc. What does the stack machine model mean? And those are all great ways in which you can learn about the text format. The Writing WebAssembly by Hand page is also great in that it is a very practical introduction to JavaScript. So you'll be writing WebAssembly text format, but then also running it via JavaScript. So you also have JavaScript code to link your WebAssembly to JavaScript. So this is a great way for you to understand how the link between JavaScript and WebAssembly works. Then if you'd like something a bit different, the cartoon introductions to WebAssembly on the Mozilla Hacks website are a fantastic way of just getting to know why did we actually build WebAssembly, so and what are some of its details. So for example, if you have a crash course in JIT compilers, so it explains how JavaScript is run in a compiler, but also why that is both good and bad, and what WebAssembly does differently. So if you want to get a bit of the background about why WebAssembly was designed like this with some nice cartoons, this is a fantastic way to get to learn WebAssembly. The Chris Hay YouTube channel contains a lot of videos on WebAssembly. So you get coding Fibonacci in WebAssembly by hand, a beginner's tutorials of coding WebAssembly by hand, a lot of things here that are very useful, and he explains things in a very neat and concise way. And then finally, if you're more of a book person, you could maybe try out The Art of WebAssembly by No Starch Press, and to also get a nice introduction to WebAssembly. And with that, we've reached the end of this video. I hope this introduction to WebAssembly has been useful to you, and that you're now keen to try out more of the WebAssembly world, whether that is by directly writing WebAssembly on the WebAssembly track on Exercism, or by compiling to WebAssembly and running your non-WebAssembly code in the browser. Let us know in the comments what your experiences are, because we really want to know. And we'll see you next time. Bye.